I'm going to talk about, I've given this talk a few times, actually. There's no harm in giving the same talk over and over again, just different variations on a theme. Like a great I see it like a great work of classical music, basically. Some people might have another interpretations of it. So I'm going to talk about how to calculate this time-dependent wave scattering problem from the frequency domain solution. And I'm going to focus kind of on explaining how it works. So rather than sort of highlighting all the fancy research I've done, I'm going to try and actually just give a bit of an explanation of it and how it works as simply as I can. So that may be rather crazily ambitious. So let's just have a look at I mean, there's a very strong focus on the frequency domain solution, and I understand why that is. And it's an enormous amount of work to calculate, and then the time-dependent solution itself can just be built from it, and we kind of just feel like the job's done. We're a bit exhausted by it. But I just want to, my main sort of take-home is that it's very easy to calculate the time-domain solutions. I just want to show, I think this will work. I'm never too confident with Zoom's amazing powers over the internet coming from Australia. So this is a problem. Here's the reference here. It just shows you a time-dependent simulation. And these are trenches. It's a very simple problem. These are floating plates. And you can see here, this is the time-dependent solution. So this is a pulse. And every time it hits one of these, it breaks up and they start to bounce around, all kinds of crazy stuff. Then it hits these plates. So this was and I think the reason I wanted to show this movie and the following one is just to show that you get if you looked at the solution just from the frequency domain solution, which is all it's very commonly calculated, you don't get a sense of this complicated behavior of the system and the way that it interacts. I mean, we know intuitively it's going to bounce off these things, but and you can start to see here that there's kind of waves trapped and all kinds of stuff going on. So I'm kind of promoting the idea. It's amazing that this has got as much energy as that initial pulse. Like, you're going to tell me that it can't be right. But there must be some numerical error going on. And you can see it is slowly decaying away, but of course the waves are bouncing around. But this illustrates and it shows some of the things that you wouldn't see from just a frequency domain simulation. So, and it's, here we go. I think I've probably shown enough of this movie. I don't know when it's going to stop. And here's another simulation from another paper here, which came out of a program at the Isaac Newton Institute on the Wiener. But what we've got here is a free surface and a plate, and there's a pulse that comes in, and it excites. I'm only showing the displacement. There's a fluid in here. Okay, so maybe it's hard to see the physics of this problem, but there's a plate here floating in the fluid. And what happens is that on this side, there's only one kind of wave mode, and on this other side, there's two wave modes. And you can see that when the pulse hits, some part of it breaks off and starts traveling back. And then when it hits the plate, it breaks into these two pulses traveling which have different group velocities. Okay, and they exist both in the plate and in the fluids and the plate. They're coupled together. And this, of course, this one here is you can see this one here is kind of spread more evenly amongst them, and this one here is more dominated on the fluid. So you get an insight into that from the Wiener solution, just in the frequency domain, you wouldn't have got. So I think that's just saying, okay, and these problems are nice and simple, and they're all one-dimensional. So it's not any great challenge to calculate. I like to use the computer. I like to use MATLAB and work with, I'm not doing Mathematica or anything, but I don't like to do anything too complicated or too demanding on my computer. So stick to that. And we're not interested in these sort of problems and trying to work out whether we've got to calculate the solution in some incredible accuracy. We're just interested in trying to get it to line with something like that. Okay. So here's where we start just trying to explain how this all works and the idea behind it. So here's our very simple problem of the dx dt equals mx, where m is a self-adjoint matrix. So this is something everyone, I'm just wanting to start on some very solid ground here that we all understand here how this works. So we can write the solution as the sum, and I've written it in this way here with some sort of inner product notation, maybe just to confuse us a little bit, but it's written as the sum over these eigenvectors. And it's something we teach students here in second year. It might be different where you come from, but it's the standard sort of stuff. It's an interesting. The first thing to note here is that the solution is no time stepping. So it just directly calculates the solution at all times. And you know you've got it right if you plug in t equals 0 and you recover your initial condition. So it's one of the features of this problem is you sort of get it's self-diagnosing, right? You know that you've got it right because you recover the initial condition. Okay. So if we wanted to solve this on a computer, what we'd do is we'd ask MATLAB to find the eigenvectors and eigen values of the matrix. And MATLAB's actually really clever about how it does it. And it would produce us this diagonal matrix with the eigenvectors, and it would produce this matrix P formed from the eigenvectors. And it would normalize those eigenvectors to have modulus 1. So the self-adjointness will give us the property that we can write this as the product of this matrix P, which is effectively the matrix of eigenvectors, and this P star is the inverse of that P. Okay, and this is the conjugate transpose here. Okay, so this is great, and you know, it's just another notation for what I wrote before. And the product is the matrix multiplication. All right. So what happens, give me 1 second. I'm just going to make sure I say something to my children. I just screamed at my children. Hopefully nobody heard that. I'm not sure how effective it will be. It's the joys of giving the lecture from home. It's very relaxed though. All right. So what happens if somebody should write it? If you can hear them screaming, I'll write in the chat. Others will just try to ignore them. What happens if it's a second order case? And now we have M as a positive self-adjoint. So now we're going to our wave type equations, right? We're moving a little bit further on. So in this case here, you're going to get, and this is probably not something you'd ever see written down in undergraduate courses. I don't quite know why. There's enough, you've got enough problems to cover, so just don't let this one go. But it's almost identical. You have two initial conditions: the initial value of x and the initial value of the derivative, and then you get cos of lambda t, and you get sine of lambda, the square root of the eigenvalue. All right, and if we write it in terms of matrices, it just takes the following form here, like this is almost identical, right? Here's the p, here's the p star. Okay, so all good. So what happens next? And why have I told you all this that you already know? Well, what happens if we go to something like, we go to the wave equation, right? So I've got a bit of a funny wave equation here where I've added a variable h here. It simulates some problems of water waves. I'm going to show some calculations as it makes it a bit more of an interesting scattering problem. Okay, so in this case here, the solution is written down as this. Here's the notation, and it's almost, I'm trying to match what we wrote before, but this inner product is now an integral because the functions are continuous. They're not vectors anymore. But we can write down the expansion. It's very similar. So that's all good. We're good to go here, right? So this is just a expansion in terms of the eigenvectors of this operator here, which you can calculate. Okay, and there'd be a bit of a numerical thing to calculate those. And in this case, if we did the case that I'm going to show you here, you can actually do it exactly, because I'm going to have a very simple h that jumps. All right, so here's where it gets a little bit one step further that maybe is a little bit strange. But I don't need to tell you guys that on a computer, everything's finite dimensional. There is no infinite dimensions. So we're going to choose a discrete set of points, x. So then we've got the eigenvectors that count 1, 2, 3, 4, 5, 6, 7, 8. They go out to infinity as well, which is great, but we can't do that, can we? We're going to have to stop somewhere. So we're going to stop at 1,000 or 100 or 10 or something, and we're going to have 100 or 10 or 1,000 points, and we're going to form a matrix, which I'm going to call P. So it's almost like the matrix you had before. It has the eigenvectors in one, you know, as the columns, and the rows is the X now. So in this case, when we do that in a product, that's an integration. So how do we integrate a discrete set of points? Well, it's done through some kind of integration rules, like Simpson's rules or something like that. So we get exactly the same structure appearing, except we have to add in a W, which is I've said it's a diagonal matrix. I want to write a matrix here, you know, because that's our notation, right? But it's a diagonal matrix which contains the integration rule weights, right? So if we've got lots of xi's, then the w's are going to be small, you know, because if they're, you know, because it's going to be basically the step size or something like that. So hey presto, we've ended up with exactly the same expression for the solution for this problem, right? And this is the way you should implement it on a computer. This is how you should do it in MATLAB. If you type into ChatGPT or go on searching on the internet for how to solve the wave equation by separation of variables, you're not going to see the solution written like this for whatever reason. They're going to do some kind of numerical integration or some crazy stuff like that. But it's not going to be at all efficient. But this is the way to solve it. Okay. And it wasn't totally obvious to me actually that this is the best way to do it. I kind of came to this over time to working it out. All right, so here we go. So that's cool. I'm just trying to show this movie. So here's a solution, the simulation of this wave equation. I just want to show a bit of a movie here. And so this is the change in depth here, like a shallow water equation. So there's some sort of humps here. This is just, you know, this is the H here that varies. So I've got some scattering from here. And of course I hit the wall here. I've got some kind of Neumann conditions on the wall, like it's a wall of a tank, and waves come and bounce back. All right, you get this repetition here of the solution. All right, all excitement. Okay, so that's all good, well and good. Nothing, we've done nothing too tricky here yet. Okay, so now we go to the problem where we've got an infinite domain. I need a picture here actually, which I haven't given you, so that's going to cause some confusion. But it's the same problem, except for the domain goes out to infinity. See if I can dare to. So I'm going to draw a little picture of it. So that's the domain here, and it goes off to infinity in each direction now, okay? So now we're going to have an incident wave coming in, and we're going to have a reflected wave coming back. And we're going to have a transmitted wave. And we're going to have the same problem. Waves could come in from here. It's going to be the same solution from symmetry. Okay, so this isn't a very difficult problem to solve, though. Like, good grief. We're going to have e to the I kx, or e to the I lambda x, and r e to the minus I lambda x. And then we're going to have some match here, blah, blah, blah. We're going to write down the solution. It's a dead easy problem to solve. So, yeah, I don't want to keep annotating. So this is a dead easy problem to solve, okay? And we can write down the solution as the sum. We're going to try to mimic the structure here, and we're going to write down the solution as the sum of these these solutions, these incoming and incident wave solutions. Now we've got continuous x and we've got continuous lambda. We've got a solution for every lambda. So, and then we can normalize these eigenvectors. This is how to normalize them is a little bit tricky because they're not like, you can't just calculate the integral because it goes out to infinity. It doesn't exist in all the space, function space and all the stuff, but we can normalize these and we get this answer here. So they normalize and the normalization is 2 pi, and we can write down the solution as the sum here. Okay, and we've got a sum from k equals over the incident waves from both directions. We've got an integral over all the positive frequencies, effectively. I've called it lambda rather than omega, perhaps not helpful, but that's what I've chosen as my notation here. Okay, and so there's the solution here, right? That's the solution. Now let's just stop for a second and go back to what I was saying before. about this P matrix and all this stuff. So we're going to go and try and do this on a computer. So everything's finite. So we didn't have a continuous x. We never had that anyway. We don't have a continuous lambda. We're just going to take a discrete set of lambda. So with our discrete lambdas and our discrete x's, we can form another matrix P. And then the solution can be written as this following expression here. So it's slightly more complicated than what we had before. So we got P, we've got to put in another weight, because when we do the integration back here, we're going to have to integrate over lambda. So we're going to have a weight for the lambda. Okay, so and again, it's just a simple quadrature rule. No one's going to try and do this by Gaussian quadrature or anything like that. Like you can go as fancy as Simpson's rule if you like, but you can just do it by the midpoint rule or something like that. So there you go. There's the expression here for the time-dependent solution. You can just directly calculate it from the frequency domain, form a matrix out of it, and multiply it up. So at this point here, my job is done, because that's all I wanted to explain to everyone is that once you've calculated the frequency domain solution, form it into a matrix. You might find this x is or the lambda has multiple dimensions, right? But then just order them as you would. Right, so you're just going to go, in some way create a one-dimensional ordering of your x's in three-dimensional space. You're only allowed a finite number, so that's not a drama. And the same with the lambda. Form this matrix up and then just multiply it out. You're going to get the solution in the time domain. It's as simple as that. There's nothing more to it. Plus or minus the few little tricky bits about diagonalizing it. And you've done it right if you put in the initial condition. So if you find that this whole sum here, I'll have another go with my annotator. I quite like that. If this whole product here is the identity, right? Then you're good to go. Sorry, with this we'll get rid of that. Make that the identity. That product there is the identity. Okay, then you've done it right. It's pretty, and there's no time stepping in this, and that. It's actually, if you can get the initial condition right, you've got everything right. All right, clear all my rules. So I can continue on, or I can stop here. I've told you this. So what happens if we go to something more complicated, I guess, is the only thing here. I'll just show you this picture here. So here's a simulation on the infinite domain. So we've used that formula, and I've only discretized, and I've only allowed x to live in this domain. It's not perfectly matched layers or anything like that. I've just got the solution here. I just don't ask it to calculate the solution out here, because I'm not going to show you it. But the solution it's interesting that it's, at the beginning, it behaves exactly like that finite dimensional, the solution with the walls, and then it flows away here like that. All right. So this whole solution is just built from the incident wave solutions, the scattering solutions from this problem here. I haven't given you any of the physics about this problem, but it's some kind of simple jump condition here. That you've got one wave speed here and another wave speed here. All right. Okay. So every linear problem can be solved in the time domain by forming this matrix product. I put a question mark there because I've never found one that can't. And you can get pretty crazy on this if you want. Like you can add in different materials like plates, which have completely different behavior, and the inner products get shifted radically. So it's not just a simple, there's some sort of simple quadrature rule. It's got to be something a bit more sophisticated, but it's still a matrix product. So, plus or minus that weighting. And a lot of it hangs in that weighting. It says it helps if the operator is positive and self-adjoint. Most people deal with positive self-adjoint. Positive's great. Everyone should be positive. It just means it's energy conserving. So once you introduce something that's some sort of loss into the system, it can become more complicated to do it. It probably is still possible, but it's not entirely sure that you can do it, because it's just, if you have a very lossy system, can you send a wave and it might never get in? And I just written down here, so it does generalize, and I've written down here all of what I've written is known, but dot dot dot, because it's, I'm not sure I've never quite seen it written down the way I've written it down, but I'm, like everything, it's bound to have been done somewhere else. I just don't know. I haven't found it. I mean, you haven't done something important if someone hasn't already done it before. Been some advice to never be upset when you find you're not the first person to do any piece of research. All right. So just going to look at some other problems here for a few minutes, and then we'll go on and have a little bit of a look at this some singularity expansion method and some stuff like that. Okay, so this is the wave equation in an interior domain. You know how to do this. It's like so one of the key points is about this idea of compaction and non-compaction. If we want to get into the maths of it, so when we have a compact region, we have a compact operator, essentially. It's not quite the definition, and a compact operator can be approximated by a matrix. And when we have a compact operator, that's one of the definitions of compact operator. Now, when we have a compact operator, we get this lambda, we get this discrete spectrum, and we can sum everything up, and everything becomes really nice. We have continuous X, but we don't have continuous frequencies. We have these discrete frequencies. So it's really interesting to go, okay, if you go to a non-compact operator, which is what I just showed you, according to pure maths, you can't approximate like that by a matrix. So how the hell did I just pull off that solution? I've violated their theorem. And it's not entirely sure what the answer to that is, but the point about it is something like this, that we're not interested, there's some other thing that we're interested in the sense that we're interested only in some finite region, and we're interested only in some initial condition that has some kind of property, like its curvature is limited. It's not, like if I make the initial condition more and more wiggly, I'm going to struggle to approximate it. And if I push it further and further away in the domain out to infinity. But it's provided that we start out and we're only interested in some finite region or something like that, then it does seem to be possible, even though you shouldn't be able to approximate it by matrices. All right. So then we go to the wave equation in the exterior domain. So this is about a super simple problem, right? It's just Neumann scattering, say, from cylinders. That's what we're going to look at here in the time domain. So there's the, so in this case here, all right, now I've yelled at the 17-year-old to go yell at the children to be quiet. It's a big parent. All right, where was I? So we've got this, we're solving the wave equation in the exterior domain, right? Now we've got a continuous spectrum, and we've got incident waves that are Bessel functions of different orders, and we're going to have T matrices if we want, right? That's how I solved it. And we're going to use Graph's addition theorem and all that kind of stuff. So then we have this, so now we've got this continuous spectrum, and we've got this index with an n and a lambda. Okay, so when we form up our matrix, our big matrix to do the time dependent solution, we're going to have to kind of form this in a long sort of, we've got 2 dimensions, but we're just going to have to order them in some way to make a matrix. That makes sense. We've got 2 dimensions in X and 2 dimensions in the spectral parameters. And what you can do in MATLAB or in any, I'm sure in any program, I don't know other programming languages, right? I'm too old to be, and too lazy, but you can just resize the matrices. You can start out with an array, resize it, and multiply it out. All right. So then there's this weird result about this normalization of these eigenfunctions, because how do they normalize? And this is the trickiest part about this. And there's this sort of very general result here. I've quoted this Walcott 75. I'm not actually sure I've ever read that paper, but I must have, I can't imagine I made it up. But basically, when they normalize, you can remove the scatterer. And it's essentially an energy argument. You've got the normalization. When you get the direct delta function, you've gone to infinity. So you're only interested in the infinite part about the energy, and the scattered part doesn't have an infinite amount of energy. So you'll end up with this the normalization as though there was no scattering, and then you can just use the formulas. I mean, who knows how to prove that these Jn's normalize like that? That looks like a real kind of pain in the neck of a calculation to do. So then we write, and then we've got the solution here written in the same sort of form, and we can just convert that to those matrices and multiply it out. So, and I sort of said this is not at all well known. It doesn't seem like it's a common thing to just take the frequency domain solution for these multiple scattering by cylinders or for whatever heck crazy shapes you want to scatter and calculate the time-dependent solution. All right. So, just look conscious here. I'm really going a bit slower than I thought. So let's get my foot down. So we can do some long time approximations. I just want to talk quickly here about this, the structure of these equations. So every time you solve a wave scattering problem in linear, you end up inverting a matrix. Okay, that always happens. There's always that invert the matrix step, unless always is the dangerous again. Sometimes you might have a one-by-one matrix, one-dimensional matrix, but so you still are inverting a matrix. But generally, you end up inverting a matrix like this, and this is some numerical approximation of some infinite dimension. It's something. This matrix depends on some number, right? That's growing with the discretization. So what you've got, this operator here always appears. This one, and I've written this identity. I've pulled it out. Sometimes you get lambda squared times that identity. It's not always the same. Sometimes you might end up with this m. Okay. So when you calculate the solution in the frequency domain, what you do, this is always the case, okay? So this is some real general structure here. You form an inner product, which is like a matrix of at each, for the calculated at x, you solve this problem. So this might be your solution in terms of Bessel functions or some T matrix or some very abstract way. It's not actually the value at any x. It's at values of the coefficients in some expansion. So to convert the coefficients in that expansion that you've calculated, you do an inner product with respect to some vector, which I've called W. Okay, so this is the universal structure here. So you can see that what this n x of lambda is totally dominated by this matrix part. And this f of lambda is not super important. It's dominated by this part here. So the analytic extension of this operator is super important. So this is, so I've jumped about several stages down here perhaps, but so we're now thinking about in the frequency domain, this general structure that we can analytically extend this operator, and then we search for the zeros of that. Those are the resonant scattering frequencies, all that sort of stuff. Okay, and we look, and near a simple pole, we can approximate this operator in this form here. Okay, where we have the derivative of this matrix appears. You can calculate this numerically. I have to go through this a little bit quickly. There's a hell of a lot. And you end up with there's a little bit of stuff. If you plug all this into the formulation I've given you before, you end up with an approximation to the solution in this very low dimensional mode that's a projection onto these scattering frequencies. And this is, so anytime you get the sort of bouncing or scattering or any kind of trapping, like I showed you in that first movie, you can approximate it in this low dimensional space. So this is giving us a low dimensional approximation of the solution. All right. So hopefully I can show this, illustrate this problem here. So this is the, I call it generalized eigenfunction. This is the full time dependent solution. So I'm hitting this thing with a pulse. This is 4 cylinders, and I'm looking at like it's a wave moving up and down on an ocean. So there's 4 cylinders that are symmetrically arranged, and of course 4 cylinders have this highly trapped wave inside it. So when this thing hits, the after a long time, we start to close the contour in the appropriate way, and we end up getting onto this essentially one-dimensional solution. And this is the projection calculated on it. So it's a way of sort of, it's called the singularity expansion method. It's a way of getting these long time approximations in these very low dimensional systems. And effectively, these systems are transitioning from towards a compact operator. Like if these cylinders touch, you'd have a compact operator, and this would be one of the modes of vibration inside it. Let's have a look at this problem here. Okay, this is a bit more interesting because we start with an initial condition. We displace it initially. We don't send it in by a pulse. We just displace it and let go of it. So the energy runs out, and some of the energy is left trapped between these cylinders. And here's this projection here, and you see they start to become the same. All right. There we go. And then I'll just show you what this is the equivalent problem with 9 cylinders. Okay, it's a bit more interesting. So there it is flowing out. And then you get stronger trapping with 9 cylinders. And of course, this goes on and you end up with we're getting onto these, band gaps and all this jazz for these periodic media. And these are all tied up with these resonances. It's actually another way to look at them. But the initial condition, we just started out with some displacement, energy ran away, and we're left with this part that's trapped. And this is the singularity expansion method. And it's interesting and kind of beautiful what happens here, because there's lots. It breaks into 4 different modes. 2 of them are identical, under rotation, and 2 of them are the other 2 are different. So like they're either all moving together or they're out of sync. And the energy moves around between those because they have slightly different rates of decay. So these are modes of vibration that also have a decay. They have a complex part that came from the singularity expansion method. All right. I don't know how much more to talk about these, a few other problems that I've applied these same methods to. They're all in water wave problems. So if you're not familiar with water waves, they're, you've got this, they're a interfacial wave at the surface. So it's the solution of Laplace's equation. So what happens is it just becomes a little bit more complicated because you can use Laplace's equation to project onto the surface. Right, if you know everything on the edge and you've got Laplace's equation, you know everything everywhere. So it just becomes a bit more of a complicated process to try and write down all the expansions. And a lot of my calculations were for these more complicated case rather than for that simple wave equation. I didn't, actually never solved for that in any sort of publication because that sort of seemed too simple. But in terms of presentations and things, it sort of makes sense to look at that, because it's simpler to understand. Okay, yeah. I think I'm just going to skip through this. You have to get into this abstract wave equation where this is a Dirichlet and Neumann map, but it essentially is still a positive self-adjoint operator and all this stuff. All right. And you get the solution written exactly the same form as always. So here's a solution here calculated. Okay, so we've got what is called a dock. It's just a rigid thing sitting on the surface of the water. So, and if you looked at that initial condition when I started this problem out, there was some kind of slight kinking here. It actually wasn't completely accurate at the start because I hadn't actually discretized this enough. So it's one of the weird things about these solutions is they you get the most inaccurate part of the solution is at the t equals 0. But you can see what happens here is that the low frequency part, they can propagate under here. If you know anything about water waves, they have a depth and it depends on the wavelength. So a 10-second wave has a wavelength of about 150 meters and it extends about 50 meters into the fluid, and then it sort of scales from there. So these high frequencies are bounce around here and are sort of trapped. You can sort of see how this kind of feels like this transition between and if this went out to infinity, they'd be perfectly trapped. They can ever so slowly radiate energy away. All right, I'm going to leave all that. I don't want to give anyone from their coffee. This is a bit stranger here. This is something which is a moving body, and you can again simulate that here. And it's kind of a weird thing that I'm sending in all these very strange waves from infinity to create that initial condition. You can see the rippling here. It's not quite right. So that's because when I discretized in frequency, I haven't gone up to the very highest frequencies. So this is the motion of a rigid body. I did just want to say one last sort of thing here. Okay, maybe a step too far I've written. I would want to come to this because if you just look at this very abstract problem, there is another way to tackle it. So we've got M as a positive self-adjoint operator. So this could be any of those operators we've seen, and loads of you are solving from positive self-adjoint operators. Okay, if you're doing wave equations and you've got energy conserved, then that's what you've got. So you can solve it by Laplace transform, and you get the solution like this. Because this is positive and self-adjoint, we know the spectrum's all on one side, so we can the Bromwich contour, we can pull it right up to wherever we want. So I pulled the Bromwich contour right up, and then I've spun it over. So I get an integral like this. It looks a lot more like a Fourier transform, and it's and these are actually the lambda's real. So it's like this is like the frequency domain solution. If you solve for e to the I omega t or e to the I minus I lambda t, you'd end up with this. So this is sort of like the frequency domain. So it's super close to. Okay, so just say this again, just to be really clear that all these problems that you've got, loads of people have got, involve the second positive self-adjoint operator. So we can solve it another way. And because of that, we know all the spectrum lies on one half. So we can use a Laplace transform, but instead of doing it with e to the st, we do use I lambda, more like a Fourier variable, and then we can flip and we get like a Fourier transform here. And you can go into the theory from here. This is quite a good launching place to try to understand a whole lot of stuff. And you can calculate, and you can see here that, okay, I've got before I had an identity here plus m, remember that? So I've written in, this is just, how the hell I want to write it in a sense, but this is exactly that operator that we talked about with the analytic extensions. So it just appears here. Maybe it's a very sort of natural place to end up. Okay, but it's not that in this case here, you're not solving the frequent, you don't have the incident wave. You don't have a notion of a wave coming from infinity when you're solving this. You actually need to have some radiation conditions like you apply here the Sommerfeld radiation conditions, and they arise naturally because you've come up to that Bromwich contour from one side. Okay, so that you have to take it. So this is starting from these are the initial conditions written down there. And in some ways, there's not a hell of a lot of help writing it so abstractly as that, which is why I just wanted to mention that here while we're on this topic, because you might sometimes see this done as well. If you start looking into the time dependent, you'll come to that from this angle as well, I'm sure. All right. So I'm going to finish there, and these are my conclusions. Hopefully you've learned something, and certainly perhaps some of you already knew that you could write this time-dependent solution from the frequency domain as this matrix product that so simply generalizes what happens in finite dimensions. But it wasn't obvious to me, and I've never seen it written down. And then we talked about this analytic extension. I didn't really get too far into that, but that's another whole topic. But they're highly connected because of the formulas you write down. They just plug these analytic extension just sort of plugs naturally in. It led from the contour integration straight onto the projection onto poles. And it does seem to generalize wildly. I've never seen a problem it doesn't actually apply to where you've got energy conserved. Okay, which that's the key point. And then, all right, I'm going to stop there. Thank you very much. Yeah, exactly. Well, because yeah, exactly. Well, it's like so if you've got some kind of nice Gaussian that's just got like a single hump that goes from -1 to 1, you can probably represent that Gaussian pretty accurately with 100 points. So it's really about the initial condition kind of sets the scaling. So that's one of the things that, so it's highly dependent. If your initial condition is highly variable, then you're going to need a whole lot of points to calculate that. So it's actually you kind of, the problem's kind of set up by that, but it's a little bit more complicated. That's in the physical, that's the X space. In the frequency domain, it becomes more complicated because, for example, when I showed you that problem with the dock, if you suddenly let something go impulsively, it can create a lot of high frequencies. So then you need to go, but it's, you sort of need to have an intuition from the initial conditions, what kind of frequencies it's going to make. There's no way that I know of automating that. It's like it's sort of like a thing that you fiddle. I mean, there might be a theory of it, but it's not something that I know about. But it's just about the kind of the initial conditions themselves, and using that and like having some intuition about it. No, not at all. No, and all I've done is I mean, because I basically get my computer and I run it from frequency 0, 0.1, 0.2 up to some point where I just sort of figure it's going to give up and I've run out of energy, and then I just use only that. That's the only approach I've ever taken. I've never thought about just, and essentially the kind of schemes I'm using start to run out of energy. They're not going to be able to do super high frequencies. They start to break down. So yeah, so it's just everything's done. All the integration's been done with all those calculations. I just use it's always a discrete set of points, and it's always like a midpoint rule or something. Maybe Simpson's rule is fancy if I've got. Have fun. I wish I was there.